Okay, good afternoon, ladies and gentlemen. My name is Adunim Paipoon from Rubber Technology Research Center, Mahidol University. As you can see on the screen, my presentation today is a topic of newly proposed actions of hydroxylamine on the inhibiting storage hardening of natural rubber. First of all, I would like to introduce briefly my workplace, Rubber Technology Research Center. We are the specialist center for rubber science engineering located at Mahidol University Saraya campus. We are working on technical service of testing for the raw rubber compound, and rubber products. And we do contract research and give advice to many companies. And we organize training courses covering all about rubber. Anyway, my presentation today is divided into 4 parts that are introduction part containing natural rubber, storage hardening phenomenon, and the origins of the research, followed by experimental results and discussion, and lastly, conclusion. Let's begin with introduction. Natural rubber, or NR from Hevia brasiliensis, is a colloidal system of cis-1,4-polyisoprene suspended in water serum. NR is not only cis-1,4-polyisoprene, but it also contains some non-rubber components such as proteins, lipids, carbohydrates, inorganic matter, and so on. NR is a good material from renewable source. It is eco-friendly material with good balance of outstanding properties such as very high tensile strength and high growth resistance. So NR can apply for various applications such as food waste and growth. This slide shows the fundamental structures of NR. NR is long-chain cis-1,4-polyisoprene. Connect with 2 trans units. At the initiating end is omega terminal composed of modified dimethyl allyl group that can link with proteins. At another side is alpha terminal consists of mono or diphosphate group linked with phospholipid by hydrogen or ionic bonding. From this structure, NR can form the natural network by the interactions or branch point of proteins and lipids at the initiating and terminating ends. Thailand is the world's largest producer and exporter of NR. So the research work on NR in Thailand is necessary to realize the full potentials of uses. But the big disadvantage of NR to restrict the uses is storage hardening phenomenon. That is the origins of the research. What is storage hardening? Storage hardening is the characteristic phenomenon of NR when keep NR under ambient condition, in which NR become hardened. The storage hardening can be detected by the increase in gel content, plasticity, and Muni viscosity. At present, the actual mechanism of storage hardening is not clarified yet. Storage hardening makes NR difficult to control the consistency in properties and make NR need more power consumption and longer time for mixing NR with other ingredients. Although the storage hardening, the mechanism of storage hardening is not clarified yet, but the most accepted assumption is the condensation between aldehyde group present on NR molecule to form the undone condensation reaction. So the storage hardening can be suppressed by the using of the reagent that can react with aldehyde group, such as hydroxylamine, dimidone, semicarbazine, and hydrazine. But in the case of hydroxylamine, it was believed to react with aldehyde group to form the oxime structure that the andon condensation could not proceed further. However, by using advanced technique like NMR, there is no evidence to show the presence of aldehyde group on the NR main chain. The presence of aldehyde group was further studied by using fractionated NR to fractionate NR into various molecular weight. It was found that aldehyde group increased with increasing molecular weight. That means aldehyde groups are not autooxidative degradation products of NR. Moreover, it was found a similar distribution trend of aldehyde and ester group. It indicates that aldehyde might be derived from unsaturated fatty acids of phospholipid bound to NR. In order to confirm this assumption, the NR was subjected to transesterification reaction to remove phospholipid. It was found that after after the transesterification to remove lipid, the aldehyde content of NR decreased to the same level as synthetic polyisoprene. This confirms the presence of aldehyde group on the phospholipid molecule. The effect of non-rubber on storage hardening was studied under phosphorus pentoxide condition. It was found the increase in plasticity in the case of FNR, fresh natural rubber, as a control, DPNR and CNR, that the proteins were removed. But in the case of TENR and TEDPNR, that lipids were removed, we found a constant in plasticity. This indicates that protein is not responsible for storage hardening, but phospholipids are the essential factor for storage hardening. So the aim of this work is to acquire better understanding of role of hydroxylamine involved with phospholipid at the rubber chain ends. This study was divided into two main parts. First, a model study of alpha-fetidylcholine. The reasons for using alpha-fetidylcholine is because alpha-fetidylcholine is the most abundant phospholipid found in natural rubber. The alpha-fetidylcholine will react with hydroxylamine directly and then characterized using FTIR technique. Second, the effect of hydroxylamine on the structure and storage hardening of NR, studied by using deproteinized natural rubber latex. The reason for use deproteinized natural rubber latex because we want to remove network or gel formed by protein that might interfere our study. After we obtain deproteinized natural rubber, we did hydroxylamine treatment using hydroxylamine hydrochloride at room temperature for 1 hour to obtain HDPNR. And we did transesterification treatment using sodium methoxide in DPNR solution at room temperature for 1 hour to obtain TEDPNR. All samples were cast into thin film and then characterized for ester content, gel content, molecular weight, proton NMR, intrinsic viscosity, Huggins K constant, and green strength. The storage hardening was tested using P2O5 condition and then characterized by monitoring the change in Mooney viscosity during testing. Let's move to result and discussion. This slide shows model study on cleavage of alpha-fetylcholine using FTIR technique. The FTIR spectrum of alpha-fetylcholine shows the characteristic band of ester. After hydroxylamine treatment, the characteristic peak of ester disappear, and we found the peak of amine corresponding to fatty hydroxymic acid. This result indicate that hydroxylamine can break the linkage of phosphatidylcholine at C1 and C2 position and liberate the fatty acid, hydroxylamic acid, and glycerylphosphocholene. The contents of long-chain fatty acid and intrinsic viscosity of DPNR after hydroxylamine treatment are shown in this slide. It was found a decrease in ester content to 1/2 after hydroxylamine treatment. This indicates that hydroxylamine can decompose the phospholipid at the chain ends of the rubber. Since branch point can make NR a very long chain, the viscosity of NR is high. If the decomposition of branch point occur, the intrinsic viscosity should decrease. This result shows the ester content together with intrinsic viscosity decrease after hydroxylamine treatment. The result indicate that hydroxylamine can decompose branch point formed by phospholipids. The decompositions of branch point can confirm by NMR technique. The spectrum of DPNR show the signals of mono or diphosphate group and phospholipid at the terminating ends of the rubber molecule. After hydroxylamine treatment, the signal of phospholipid disappear. This confirms that hydroxylamine decomposed phospholipid at the alpha terminal group of NR. The structural characteristic of hydroxylamine treat depolarized rubber was compared with DPNR after transesterification treatment. That is the common method to remove phospholipid. The results show that ester content and molecular weight decrease after hydroxylamine treatment and transesterification treatments. And the shift of molecular weight from high to low can be seen clearly in this chromatogram. If the decomposition occurs, you can see the liberations of linear molecule proved by the Harkin K constant. In the case of DPNR, show the Harkin K constants around 0.6, referring to the branch molecule. But in the case of the rubber after transesterification and hydroxylamine treatment, shows 0.3 of the Harkin K constant, referring to the linear molecule. So these results indicate that hydroxylamine can decompose branch point formed by phospholipid to liberate the linear molecules. This slide shows the strength properties of vulcanized rubber. We can see the very low green strength in the case of hydroxylamine treat rubber and rubber after transesterification. That might be due to the decomposition of branch point, and that might be the reason why the rubber that treat with hydroxylamine show the excellent processability. The storage hardening were tested under P2O5 condition. It was found the constant Mooney viscosity in the case of HDPNR and TE-DPNR. The results indicate that the lack of phospholipid in HDPNR and TE-DPNR make NR has no storage hardening. So from all above results, it can be concluded that hydroxylamine can decompose branch point derived from phospholipid at the alpha terminal group of NR to liberate the linear molecule. And apart from the reaction with aldehyde groups, hydroxylamine can inhibit storage hardening in NR effectively since it can decompose phospholipids. This was already published in the Journal of Applied Polymer Science. If you want to see all detail, you can read this paper. Last but not least, I want to acknowledge Mahidol University, Thailand Research Fund, and Thai Rubber Latex. Thank you for your kind attention.